Welcome. I am Professor J. N. Mandal, Department of Civil Engineering, Indian Institute of Technology, Bombay. Last time I showed you that sedimentation calculation for sedimentation analysis. Now you know that hydrometer, and this is the hydrometer, and this is the bulb. This portion is the bulb, this is the bulb, and this is the stem. So from the hydrometer you can take the reading. So if height of the bulb is the h, you have to take the reading from the center of the bulb, and then you can read the hydrometer RH. Now this hydrometer you have to be inserted into the cylinder 1, in which that water or the any liquid suspension will be there. So this is the hydrometer, and this hydrometer you have to insert it into this cylinder, in which distilled water or water suspension will be there. Now you have to take the hydrometer reading, this hydrometer reading, you insert it and take the hydrometer reading at total elapsed time of half, 1 and 2 minutes without removing the hydrometer. After the 2 minutes reading, then remove the hydrometer. This hydrometer you should remove it without disturbing the suspension, and place it in the neighboring one cylinder. So another neighboring cylinder is there, in which distilled water only should be there, this distilled water. So you have to place this hydrometer into this neighboring cylinder containing only distilled water, and arrange it by twisting motion, this one, okay. And if you wanted to remove any soil particle that may have settled on it, take the subsequent reading after the period of 5, 10, 15, 30, 60 and 120 minutes, and record it the temperature of the soil water suspension using the thermometer, and leave the suspension as such for reading to be taken after 24 hours and 48 hours. So this is the table which it has been shown that after different time, it is here, different hydrometer reading is taken under the different time. So you have to take the reading in different time, and you have to measure the what should be the hydrometer reading. So how can you take the hydrometer reading? Before this hydrometer reading, it is necessary to calibrate the hydrometer. So how to calibrate the hydrometer? So your calibration of hydrometer is essential. So for example, that this is the hydrometer, and this height of this hydrometer is 12 centimeter. So, half of this about 6 centimeter, and from here it is 7 centimeter, and this hydrometer, this reading 1.030, 1.025, 1.020, 1.015, 1.010, 1.005 and 1.00 and 0.995, and this distance is 2 centimeter interval. So, you can take any reading of hydrometer, and then you can draw this from this is x axis, this is height from the center of the bulb of the hydrometer reading, and this is the hydrometer reading. So, for example, that if you want to, for any hydrometer reading, if you want to take at this location, let us say this is 7 plus 2 9 plus 11, and then you can read the hydrometer reading 1.020. So, similarly for this 11, if you go for the 11, and then you can have the hydrometer reading 1.020. Like that, for any location you can calculate that what will be the hydrometer reading. So, this way this hydrometer has been calibrated, and for the different hydrometer you can have the different types of the calibration chart. So, this is important, and then you can take the reading and can determine that what will be the reading for the hydrometer. Now, how to calculate the meniscus correction? So, here I am showing this is the hydrometer, and this is the distilled water, this is the cylinder. So, you inserted the hydrometer into this distilled water. If you insert this distilled water, you can see here you can have some meniscus correction. So, this meniscus correction is to be added. So, this is the Cm. So, here in this table also this meniscus correction, here it is, this meniscus correction Cm is designated Cm, and this we are having 0.0004. So, this way we do the meniscus correction. Now, there is another correction which is called the dispersion correction. So, similarly for the dispersion correction, so if required to insert this hydrometer into the 100 cc of dispersing agent added in 900 cc distilled water. So, here is a dispersing agent is added into distilled water, and then you are having the dispersion correction which is designated at CD. So, this dispersion correction has to be subtracted. So, this way the CD has been determined. So, one is case of meniscus correction, this is entirely the distilled water. In case of the dispersion correction, because you are putting some dispersing agent into the distilled water and measure the dispersion correction which is CD. And in this table also it is showing that dispersion correction here, dispersion correction CD is equal to 0.0034. So, this way this dispersion correction has been measured. Now, another important that how you have to take that hydrometer reading and what should be the effective depth of the hydrometer. That means that H or ZR or HE. So, this is the cylinder and this is the suspension liquid are there, then you are inserting the hydrometer into the suspension liquid. Now, initially the hydrometer was here. Now, when you insert the hydrometer into the suspension liquid, then it moves up, and this volume from here to here, this volume will be VH by A. This is volume of hydrometer and this is cross sectional area. And in the bulb, this will be VH by 2A, VH by 2A. So, if the initial position is here to here, then final position is B to B1 to A1 to A1. So, this distance is equal to H, and this distance is equal to H by 2, and this is VH by 2. So, this is due to the effect of the hydrometer immersion. Then how you calculate the hydrometer immersion and how you take the reading for RH. Now, this sedimentation jar before the immersion of the hydrometer is this location. So, you have to calculate what will be the effective height, that means HE or ZR or Z. So, this height HE will be equal to, from here to here is VH by A, and this distance is equal to H, and this distance is H by 2, and this is VH by 2A. So, what we can write from here, that H of E will be equal to H plus H by 2 plus VH divided by 2 of A, this minus VH divided by A. That means, this will be H plus half of H minus VH divided by A. So, you can calculate the effective depth H of E with this equation. So, this is constant half, because this is hydrometer valve, this is volume of the hydrometer, and this is cross sectional area. So, this is constant. So, this can vary. So, from this hydrometer reading, you can see here, this is your what you call H, and this is H by 2, this is H by 2, and this is VH by 2A, this is VH by 2A, and then minus VH, because we are taking the reading from here to here. So, minus VH by A. So, that is why the HE will be equal to H plus half into H minus VH by 2A. So, this is the immersion of the hydrometer. So, this is the effect of the hydrometer immersion. You have to take the reading from this equation. So, this value, hydrometer reading value, this is shown here, that we designated at Z at a particular time, let us say 15 minutes, and you are having that HE or the Z value about 16 point something like this. Okay. So, you can measure that what should be the hydrometer reading. Okay. Also, you require some temperature correction. So, because we have considered the temperature correction, or you can determine that viscosity of water at different temperature. So, if the temperature is, let us say 28 degree centigrade, and then viscosity of water in poise 0.008360, and this viscosity I can also show you later that this value also has been added, this viscosity value, that is equal to the eta, and that depend upon what will be the temperature, because you said insert the thermometer into the suspension liquid and take the measurement of the temperature, and you can add if it is more than 27 degree, or if it is less, then you can subtract it. So you can do all the correction. That means you require for the meniscus correction, you require for the dispersion correction, you measure the temperature and you determine what should be the viscosity of the water, okay, at that particular temperature. Now you have to calculate that what should be the H, that is Z divided by VH by 2A, and then that you can calculate for a particular time. So you can calculate that H. Now you have to calculate that V, that is H by T, that is centimeter per minute. So V can be calculated, that is H by T, and here H by this value we are calculating V here this value we are calculating. So we know that what is H, that is H, this is the V, okay, this is V value. We know that what is the H, we know that what is the time. So you can calculate the V by H. So V by H is equal to H is equal to 14.7718, and this divided by, that is 15 minutes time. So this will be about 0.9847. So this is the V. So here that V is showing about 0.98. Now you have to correct the applying the dispersion correction, Unicode for dispersion correction. So dispersion correction, let us say R will be equal to 1.0104 minus 0.0034. So this will be 1.0070, because that dispersion correction CD we have given 0.0034. So here that here the dispersion correction is 0034. So you have written that 0034, and so R will be equal to 1.0014. That means whatever the reading you have taken here 1.0104 and minus this dispersion correction, that is this is the CD. So under the dispersion correction, so you can correct this dispersion correction. Now you have to calculate what should be the particle diameter, that is D. So this is dispersion correction. Then also you can calculate that what will be the R value also, that water value is this one, that is that RW is equal to 0.996. So this R is R minus RW is this 0.0016. Now you have to calculate this particle diameter, that is D. So particle diameter D can be written as 10 into root of 18 into eta, this divided by 980 into 60 into GS minus 1 into root of h by this is t. So, that means this is 10 into root of 18 into eta is 0.00836, which I showed you from this at a particular this temperature, this viscosity is measured, eta is 0.00836. So, this value we have taken eta 0.00668. This divided by 980 into 60, and this specific gravity of soil is 2.54, this minus 1, this into h by t. H by t you have calculated, that is 0.9847. H by t already you have calculated earlier. This is here, the h by t 0.9847. So, this is 0.9847. So, you can calculate this, and then you can have 0.128. So, this is the particle diameter. This is particle diameter. Particle diameter. So, then you can calculate particle diameter. You can see for a specific time, this diameter is 0.0128. Okay. So, this particle diameter is shown. Now, you have to calculate the percentage final. How we calculate the percentage final? That means percentage final is designated as N. So, percent final. So, this percent final is designated at N is equal to GS divided by GS minus 1 into Vs divided by W of S into R minus R of W, this into 100. So, you know that GS is 2.54, this divided by 2.54 and this minus 1 into that volume of suspension is thousands, and this 52.8 into R minus RW. R value and RW value also is recorded. This is here, you can here you can see that this is the RW value. Okay, this is R and this is R minus RW, and RW value is given 0.996. So, this is R minus RW value also given. Okay. So, this is R minus RW. Okay. So, R minus RW, that means 1.0070 minus this is 0.996. So, you can write this 1.007 minus 0.996, this into 100. So, this you can determine what should be the N value. So, N value will be 35.35. So, you have to calculate also that N dash value, which I mentioned here, defined value is equal to N into N of G of dash divided by 100. So, this N value is 34.35 into N dash G value, which we have calculated earlier, that the gravel analysis at the end, what will be the value left, percentage of final. in the gravel. So, that is you can see earlier that this will be 45.7, this divided by 100. So, this will be equal to NS will be equal to 15.7. So, this NS value is shown is 15.7. Okay. This way I am just showing one of the specimen for a particular time 15. So, you can calculate what is the hydrometer reading, then how you can do the meniscus correction, you can calculate that what should be the effective depth, then you can calculate HZR by VH by 2A, you can calculate the V H by T, you can calculate R, okay. Then you can R minus RW, then you can calculate root of H by T, and then this diameter percentage final and corrected percentage. This is the corrected percentage of the particle final. So, this is the corrected percentage of the particle final. So, for the different time you are calculating what will be the corrected percentage final, and you know that what should be the diameter also. So, from this table now from this table you can draw that what will be the gain size distribution curve of the soil. So, gain size distribution curve it looks like this, and this part is for the gravel analysis, and this part for the sand, from the sand analysis, and then this part is for the hydrometer analysis. So, this is the relationship between the gain size in the x axis in millimeter, this is in the semi-log scale, and this is the percentage final in percentage. So, from this gradation curve you will be knowing that what percentage of the gravel or what percentage of the silt or the clay or the sand is there in the soil sample. So, this gradation curve is very important. So, from this gradation curve you can determine some different parameter, and some of the parameter is called that effective size, is equal to D of 10. You can calculate that uniformity, that is coefficient, and that is denoted as Cu. Cu is equal to D of 60 divided by D of 10. You can calculate also the coefficient of curvature, and that is designated as C of V. So, Cv is equal to D of 30 square, this divided by D of 10 into D of 60. So, from this gradation curve, so you can calculate for 60% what is D60, 30% what is D30 here, and 10% what is D10. So, you know this value D60, D10 and D30, then you substitute this value here, and then you can calculate that what will be the uniformity coefficient Cu and what will be the coefficient of the curvature. And also from this gradation curve you can also that calculate that what should be the gravel. So, this gravel percentage So, as per IS code specification, gravel is 4.75 millimeter and above, and for the sand this is 0.075 millimeter to 4.75 millimeter, and for the silt this is 0.075 millimeter to 0.002 millimeter, and the clay that is 2 micron and that is 0.002 millimeter and less. And so, these are this gradation that as classification as per IS code specification. So, you can determine what will be the percentage of the gravel, sand, silt, clay from this gradation curve. Thank you.